Uh, this presentation will showcase how Group 14 in course Sustainability and Product Development developed our hydraulic cylinder. The team members are named as followed: Mikael, Pelle, Elias, Nirare and Oskar. Here's some small background information for what we're supposed to do. Since it's just a small sample, there were more specifications needed. And this is what the final model will look like. And we have marked a few points of interest. It's only a cross-section, but that makes sure that we can showcase a bit more like bearings. And about the bearing, for example, it's also showcasing the piston attachment surrounding the bearing, as well as the grease nipple, plus the lock ring that keeps the bearing in place. So that's why I brought it up. And since this is only the points of interest, we will only mention them in the presentation. For our cylinder, this is a formula used to calculate buckling. It's derived from Euler's second buckling mode. There are some differences though, and that is that it takes into account for more information than Euler's second buckling mode. It also takes into account the inner and outer diameter of the cylinder. The company Danitec supplied the formula, and the end result is that our Pmax, which is our maximum buckling force, was acceptable for a piston rod and the cylinder that we chose. We used the standard dimensions from Stacke when choosing diameters on both of them, and this was our result. For our bearings, we used the written formula, assuming a static load, since the RPM would be quite minimal. And the formula was supplied by SKF, and it also happens to be the supplier for bearings. We assumed that the factor of safety will be equal to 1.5, and that is a rough assumption since SKF gave us the estimation, so we went with that. With this in mind, the C value given was 95.7 kilonewtons, and what that gave us was a double row full complement cylindrical roller bearing, which could withstand 112 kilonewtons, since we had to place ourselves above that value. The product name of bearing is listed as there. For our welds, this is the formula we used, and it only showcases the weakest weld here and what we got. And it's the weld that connects the piston rod to a piston rod attachment, and the value was 141 megapascal, which is acceptable. The calculations for thread were a bit long, however, so we decided we won't showcase them. We did show what threads we used, and we referred to the threads on the cylinder and the piston rod then. And about the sealings, they were chosen from SKF as well, and the following list is the seals that needed to be picked. Some general rule of thumb from SKF for each seal were that they needed to be compressed a certain amount to be able to contain the pressure within this hydraulic cylinder. An example of product name is written for the rod seal, just so you can get an idea of the product names. And we decided to add a short bill of material, a basic bill of material, just so you can see what kind of products we bought and what we needed special manufacturing for. All of the ones listed as standard products were bought as were. The exceptions, however, were the cylinder house and piston rod, as it says they needed post-processing. By that we mean that we needed to use some form of lathing or milling to create the threads. Mostly we intended that lathing will be used for it in the extent possible, and I think it can actually perform threads on the inside as well. And special manufacturing, we will use lathing for the top nut and piston as well, because I think it will be enough. Finally, this is what the hydraulic cylinder will look like without the cross section. And some thoughts about the project. We obviously learned a lot about it. The amount of confusion on most subjects were a bit staggering at the start. The matter is cleared up in the end though, because it took a few days to get a clear understanding of what we needed to do. So in the beginning it was a bit trial and error until we found a working solution for the parts we needed to design. And the bearing is such an example of trial and error. We assumed it was a dynamic load at the beginning, but since it doesn't rotate much, it's obvious a static load. Also, we had a few issues with software, such as YAPDM and SpaceClaim. It took a lot of time to understand how to use it. But the plus side is that we learned how to use those programs, so that's a good thing. As some issues in YAPDM, for example, is that we created a lot of unnecessary copies of a hydraulic cylinder. But it's at least possible to see what the actual model is, so it's no issue.